Okay, now we're going to look at vectors from a slightly more algebraic approach than a graphing approach. So, first thing we want to do is we looked at how to draw something like this, where we took 3 of vector v and added it to 2 of vector w. Now we're just going to simply do it algebraically. These are called scalar multiples. This means take 3 of v, 3 times vector v, 2 times vector w. So let's look at what 3 vector v is. It's simply 3 times this vector. And what you do is you simply distribute the 3. You take 3 times the horizontal component and 3 times the vertical component. So this would be negative 9i plus 15j. And then 2w would be twice, that's a minus, vector w. So to do that, I just simply take twice the horizontal component, twice the vertical component. That would be 4i minus 6j. Now to add those two vectors, you simply add their horizontal components and you add their vertical components. So if I add these horizontal components, it's negative 5i. And if I add these vertical components, it's 9j. So it's 5i plus 9j. Okay. Now this is a little bit different quantity. This means take vector v, subtract vector w, and remember the double bars mean then find the magnitude. So the first thing we have to do is find vector v minus vector w. So what that is it's negative 3i plus 5j, and then I have to subtract vector w, and it's just, it's pretty much just like algebra. I have to make sure I distribute this negative. So this would be 3i minus 2i would be negative 5i, and this would be 5j minus a negative 3j, which would be plus, so that would be plus 8j. Okay, so that's what the vector v minus w looks like. That's the resultant vector. Now we have to take the magnitude of that vector. And if you remember correctly, the magnitude of the vector is simply Pythagorean theorem. It's the square root of a squared plus b squared. So the magnitude of v minus w is the square root of negative 5 squared plus 8 squared. So that's the square root of 25 plus 64. It's the square root of 89, and then that would be the length of the vector. So this represents the vector. By subtracting vector v from vector w, this represents the length of that vector. Okay. So whenever you see magnitude, when you ever see these bars, the answer is a numeric answer. It's the length of the vector. So what this is saying is something a little different. This is saying don't add v and w, don't add the two vectors. Take the magnitude of vector v and add it to the magnitude of vector w. So let's figure out what the magnitude of vector v is. Scoot my paper up here. Here's v. The magnitude of that vector, we're going to do the square root of a squared plus b squared. So it's the square root of negative 3 squared plus 5 squared. So that's 9 plus 25 is the square root of 34. And now we're going to add that magnitude to the magnitude of vector w. So the magnitude of vector w, here's vector w. Again, I'm going to do the square root of a squared plus b squared. So it's 2 squared plus negative 3 squared is the square root of 4 plus 9 is the square root of 13. So the magnitude of vector w, vector v added to the magnitude of vector w is the square root of 34 plus the square root of 13. And that's really all you can do with that, because remember those aren't like terms, so you can't add them. Okay, in order to add radicals, they have to be like radicals, and these are not. Now we're going to talk about unit vectors. Unit vectors are vectors of magnitude 1. Obviously, the magnitude of this vector is not 1. Let me show you what this vector looks like. Okay, this vector means I go 3 in the horizontal direction, 1, 2, 3, and negative 5 in the vertical, 1, 2, 3, 4, 5. This vector looks like that. Okay, obviously it doesn't have a length of magnitude 1. Okay, but it's really easy. I want the vector that's the same direction as this, but has a magnitude of 1. That's what it means to find the unit vector. So the first thing we have to do is find the magnitude of vector v. The magnitude of vector v is the square root of a squared plus b squared. So that would be 9 plus 25 would be the square root of 34. Okay, and so what I have to do is I have to take this vector and divide it by its magnitude. For example, if I had a vector that was 12 inches long and I divided it by 12, wouldn't it be 1 inch long? It would be 1 unit long. If I had a vector that was 10 miles long and I divided it by its length, 10 miles, it would be 1 mile long. So the unit vector is this. It's the vector divided by its magnitude. So what I have to do here is I have to do this vector 3i minus 5j, and I have to divide each by its magnitude, which is square root of 34 over square root of 30, by its magnitude, which is square root of 34. So I divide each component by its magnitude, and I rationalize this. So this would be 3 square root of 34 over 34i minus 5 square root of 34 over 34j. Okay, that's an ugly j. What that is, that vector has a magnitude of 1. It has a length of 1 and it's the same direction. So if this purple one here is vector v, the unit vector is about like this. I'll do it in pink. It's 1 unit long and it's in the same direction as vector v. So this vector is that pink one. This vector is the purple one. They're in the same direction, only this one has a magnitude of 1, the pink one, and this one has a magnitude of square root of 34. Okay, let's look at this vector. This vector only has a vertical component. It doesn't have a horizontal component. What this vector looks like, whoops, of course I didn't leave myself enough room. 1, 2, 3. This vector only has a vertical component of -3. So it's easy to find the magnitude of that vector. The magnitude of that vector is 3. Now magnitude is always positive. So if I take this vector, -3j, divided by its magnitude, it's -1j. That's a unit vector. That's a vector of magnitude 1 that's going in the same direction. It's this vector right here. It goes in the exact same direction, but it only has a magnitude of 1 instead of a magnitude of 3. And the negative is just telling me the direction it's going. It's going down. It only has a vertical component. Okay, moving on. This is telling me I want a vector and I need to write it in this form. So I need to know what the horizontal component and the vertical component of this vector is. It's got a magnitude of 8 and alpha is 45 degrees. This is telling me the direction. Okay? So what it's saying is I have this vector that goes, let's just say that that's a magnitude of 8. And it goes 45 degrees from the positive x-axis. I want to know what this vertical component is, horizontal component, sorry, and I want to know what this vertical component is. Well, doesn't it simply form a 45-45 right triangle? Right? So these are the same. So you can call this A and you could also call this A the same thing. And you can say a squared plus a squared equals 8 squared. Leg squared plus leg squared equals hypotenuse squared. So that's 2a squared equals 64. A squared equals 32. A is the square root of 32, which reduces to 4 rad 2. Or you can remember from your 45-45 right triangles that these would each be 4 rad 2. So how do I write this vector right here? This vector has a horizontal component of 4 rad 2 in the positive direction. It has a vertical component of 4 rad 2 in the positive direction. So it's 4 rad 2I plus 4 rad 2J. If you saw it written in this form, it would be the same thing. Okay, but in this case, they asked us to write it in the component form I plus AI plus BJ. Okay, let's look at the next one. I've got a vector that has a magnitude of 15 and alpha is 315 degrees. So we know from our unit circle that 315 is right here. So this drawing will not be to scale. Let's just say that there's my vector. This has a magnitude of 15. So then I have my horizontal component and I have my vertical component. And in this case, my vertical component is going to be negative. My horizontal component is going to be positive. This would be a 45-degree angle, right? Because 315 plus 45 makes 360. So again, it's another 45-45 right triangle. So A and B are the same. So you could do A squared plus B squared equals 15 squared. So 2, and I'm just going to call them both A. 2A squared equals 225. A squared equals 225 over 2. Square root. So the square root of 225 is 15 over rad 2, and then you rationalize it. So it's 15 rad 2 over 2. So my A component is positive 15 rad 2, my horizontal component, but my vertical component is negative 15 rad 2 over 2J. Or you could write it 15 rad 2 over 2 comma negative 15 rad 2 over 2 with the pointy brackets. Okay, this is called the component form. This is called the vector form. Okay. Find the direction and magnitude of this vector. So you don't have to graph these every time, but I just want to show it to you graphically. So this means I move 1 unit in the vertical. I move rad 3 units in the horizontal. I'm sorry, did I say that backwards? 1 unit in the horizontal, rad 3 units in the vertical. Okay, I want to find the direction, which means I want to know what this angle is. Correct? And I want the magnitude, so I want to know what the length of that is. So I could do Pythagorean theorem. I can say rad 3 squared plus 1 squared equals, you can call that whatever you want, c squared. So that's 3 plus 1 equals c squared, c equals 2. So the magnitude of vector v is 2. Now what is the angle? Well, we can just either A, use our unit circle, or we can say we know that the tangent, let's call that angle alpha, the tangent of alpha is opposite over adjacent is rad 3. So alpha is the tan inverse of rad 3. And so that means what angle on the unit circle has a tangent of rad 3? And if you don't remember your good old unit circle, you could just use your calculator, put it in degree mode, and go tan inverse of rad 3. And it's, oh, sorry, I didn't do tan inverse. $60 degrees. So the direction is 60 degrees. Make 60 degrees with the positive x-axis, and it's got a magnitude of 2, the length. So now this one's going to be a little different. So, and you usually want to use tangent, by the way, to do these. Okay, so this is going 6 in the horizontal. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. Never leave myself enough room. So this is 6, and this is -4. Got a right angle right there. So you can use Pythagorean theorem to find the magnitude. So you got 6 squared plus -4 squared. So that's 36 plus 16. C squared equals 52. C is the square root of 52, which is 52 divided by 4, 2 rad 13. So the magnitude of vector v is 2 rad 13. Okay, now how do we find alpha? What's the angle? Now remember, the angle is what it makes from the positive x-axis. Okay, so I know that, I'm running out of room here, the tangent of alpha is -4/6, opposite over adjacent. So alpha is the tan inverse of -4/6. Okay, so this one's going to get a little tricky on us. So second tangent, -4/6, and the negative is very important. So it's -33.69 degrees, which is this angle right here, -33.69 degrees. Okay, but we want that angle from the positive x-axis, so what we have to do is add 360 to that. So 326.31 degrees. So alpha is 326.31 degrees. Because you want always your direction from the positive x-axis. But the calculator, remember, the range of tan inverse is -pi/2 to pi/2. So if it's in the fourth quadrant, it's going to give you the negative angle. But when we're talking about direction of vectors, we want it in standard position from the positive x-axis. Okay, so let's get a couple of word problems here. It says a man pushes a wheelbarrow up an incline of 20 degrees with a force of 100 pounds. Express the force vector F in terms of I and J. Okay, so let's take a look at this. The force, by the way, is also equivalent to the magnitude. Magnitude can either be the force or it could be the length. So what it's saying is there's a man pushing a wheelbarrow up an incline. This incline makes a 20-degree angle with the positive x-axis, and the length of this vector is 100. The force and the magnitude are the same thing. Okay, what we need to know is we need to know the horizontal component of this vector, which we'll call A, and we need to know the vertical component of this vector, which we call B. Well, we simply use trigonometry to find this. Okay, we know that the sine of 20 degrees is opposite over hypotenuse, is B over 100. And so putting this over 1 and cross multiplying, I get B equals 100 times the sine of 20. So we'll write this, I guess, to 2 decimal places. So make sure your calculator's in degree mode. So my calculator's in degree mode, and I do 100 sine 20, 3.42. So B is 3.42. Now we can also use this trigonometry. We can use cosine to find A. We know that the cosine of 20 degrees is adjacent over hypotenuse. So cross multiplying, I get A is 100 times the cosine of 20. So 100. Oh, I did 10 up there. Well, let's fix that. So I did that wrong. 100 sine 20, 34.20. And then 100 cosine 20 would be 93.97. So my vector, this force vector, can be written in the form 93.97I, that's my horizontal component, which is in the positive direction, and my vertical component is in the positive direction, also 34.20J, and that's how you write the force vector for that wheelbarrow. Okay, so one more problem. Two force vectors of magnitude 30 newtons and 70 newtons, and newtons is a scientific term we use for force, act on an object at angles 45 degrees and 120 degrees with the positive x-axis. Find the direction and the magnitude of the resultant force. So we have two forces acting on an object. We have to add those two force vectors to find the resultant force. What's going to happen to the object? So it's getting pulled in one direction with one force, it's getting pulled in another direction with another force, and the resultant is going to be yet a third. It's going to go in a third direction with a different force. Okay, so I hope I left myself enough room here. So let's draw this out. Okay, I'm going to do the first one in pink. So it says the first one acts 30 newtons, so that's the force, that's the magnitude, at 45 degrees. So kind of to scale, let's say that's 30 newtons at an angle of 45 degrees. The second one, I'll draw in a different color, is 70 newtons, so it'll be more than double this length and at 120 degrees with the positive x-axis. So it looks maybe something like this. And I try to draw it a little bit to scale so that this angle right here, this has a magnitude of 70 and 120 degrees. Okay, so we want to know the resultant vector. So remember back when we did vectors, the first lesson, we do the tip to tail method when we add two vectors. Do you see how these, they share the initial point? We want to change this a little bit. So I'm going to take this vector, and on the tail of this vector, I'm going to put the tip of the blue vector. So it would be more like this. This is sometimes called the parallelogram method. Well, if I could draw straight, that would be nice. Okay, where this is 70 newtons. So I start here. This is the initial point of the first force vector, the terminal point of the first force vector, the initial point of the second force vector, the terminal point of the second force vector. And the resultant is right here if you went from tip to tail. So this is my resultant vector. That's the vector I'm looking for. I want the direction and the magnitude of that vector. Okay, so we're probably going to either be using law of sines or law of cosines here. So let's talk about this a little bit. Okay, if I connected this to this, we have a parallelogram here. Okay, so if I could figure out this angle right here, I would have a side angle side situation, and I could use the law of cosines. So let's see if we could figure out this angle right here. So think about it for a few seconds and see if you could figure out what that angle would be using what you know about parallelograms. So let me just highlight a little bit what we're talking about here with the parallelogram. This is a parallelogram. It looks like a rectangle, but it's really not. Okay, so let's talk about this corner of the parallelogram. Forget about the resultant vector. That's like the diagonal of the parallelogram. Let's talk about this angle right here. Well, we know that this is 120 degrees all the way to the blue line. And then this is 45 degrees. So if I subtract those two, this is going to give me the corner of the parallelogram. The corner of the parallelogram is 75 degrees. It's the difference between 120 degrees and 45 degrees. Now we know that consecutive angles of a parallelogram are supplementary. So if this angle of this parallelogram is 75 degrees, this angle right here is 105 degrees. And now we have a side angle side situation. And from that side angle side situation, we can use law of cosines and find the length of this resultant vector. We know that r squared is equal to 70 squared plus 30 squared minus 2 times 70 times 30 times the cosine of 105 degrees. So we're going to put that in our calculator. So it would be 70 squared plus 30 squared, oops, I'll get you on the screen there, minus 2 times 70 times 30 times the cosine of 105. And remember, that's r squared, so I'm going to square root that. I get 68.65. So the magnitude of my resultant vector is 68.65 newtons. Okay, now I need to find the direction of the vector. So the direction of the vector is going to be from the positive x-axis all the way to the purple line, to the resultant vector. So now I'm going to use my law of sines. I'm going to call that angle alpha that I marked in purple there, alpha. I know that the sine of alpha over its opposite side, which is 70, whoops, I'm sorry, it's not from the purple line, it's from here. Ignore this. The sine, this is alpha from inside the triangle. So the sine of alpha over its opposite side equals the sine of 105 over its opposite side, which we just decided was 68.65. Okay, so using our law of sines, we can figure out what alpha is. So I'm going to do 70 times the sine of 105. And I'm going to divide that by 68.65. Remember, that's the sine of alpha, so I have to do sine inverse. So alpha is 80.04 degrees. Okay, so that's what this angle right here of the parallelogram is. And again, it's from here to here. But when we look at the direction of the vector, it's the direction it makes from the positive x-axis. So this is 80.04 degrees. But now that's just what's inside of the parallelogram right there, the triangle. So to get the direction from the positive x-axis, we know that this is 45 degrees. So I have to add 45 degrees to that. So it would give me 125.04 degrees. So the direction of the vector from the positive x-axis is 125.04 degrees, and it's acting at a resultant a force of 68.65.